So once the plum pudding model was disproven, because we spotted that we have to have some big, heavy, dense nucleus hiding within the much, much, much larger atom, and that very dense nucleus had so much mass packed into it that particles would ricochet off of it if they hit. Once we got past that model, we started looking for the next best thing. And there were a couple of waypoints that we don't usually bring up. There was Nakaoda, I think is how you say his name, a Japanese researcher who came up with this model that looked like Saturn, where you had a dense nucleus and you had rings of electrons around it. But then people started to point out, yeah, but if you have a negative charge and a negative charge, wouldn't they be repelling each other? I'll point out that they didn't worry too much about all those positive charges in the nucleus repelling each other yet, and we did eventually find out that there's a reason that those positive charges stay glued together, but that wasn't really at the core of the discussion that they were having, and it's not the one that we're focused on here either. They did start to try to come up with better ideas, though, and after about, maybe about 10 years of looking, they came up with a model that looked something like this. This is the Rutherford model of the atom. Now we're saying that the electrons can be anywhere in this cloud of electrons except inside of the nucleus, obviously, because we can't have particles in the same spot at the same time. We're specifying that these electrons are always moving around. They're not sitting still at any point, always zipping around. And that means it's not going to be at all like the plum pudding model. It's not going to be a static, stationary kind of picture. It's going to be a very movement-based sort of model. We're going to be thinking about things moving back and forth and interacting. Now, under Rutherford's atomic model, we've got ourselves a nucleus right here. We've got an electron zipping around it. And I'm not going to show it zipping around because that's just too hard to animate, but you got a picture that it is. Now, it's going to be able to move between different positions around it, just like I can move my pen anywhere above the desktop. I can move it higher, I can move it lower, and to move it higher, I have to put some energy in. To drop it down, energy would come out, and that's what they're saying would be able to happen within our atom as well. Now, where does that change in energy end up going or coming from? And the answer for that, they decided, was probably the photon. They know that light comes into or out of things either when it's being absorbed or emitted. And I said it in the same order. Absorbed, light goes in. Emit, light goes out. But we can see here that that fits in this model. I started at a high energy and I can go to a low energy. I can go from a low energy to a high energy. That means to go from here to there, I'm emitting a photon. And to go from there to there, I'm absorbing a photon. There's nothing here at all specifying that I have to go between two different positions and get the same amount of energy out. It could be any change in energy. Now remember, those changes in energy are going to be related to the wavelength. In other words, the color. And if I can do any of these changes at once, then I should have white light come off of this thing. Any photon energy should be possible. But it turns out that's not what goes on. If we take hydrogen and we put it into some sort of a light bulb and pass electricity through it, what we see is in the visible range, we see that there's a red line that comes out. So red color. We're going to have some green color and some blue color. And you don't really see it here, but there's also a violet color that can come off of it too. There's also going to be these infrared lines that can come off. And ultraviolet lines. There's actually a lot of ultraviolet. Notice how high in energy it's going to be. It's below 200 nanometers, down here by 100. Remember, ultraviolet's cutoff is right here at 400 nanometers. So we're talking about some pretty deep ultraviolet right there. This is the stuff that doesn't get to us from the sun because our atmosphere absorbs it. So this is some pretty high energy stuff that would definitely give you a really nasty sunburn, if not straight to cancer. Bad stuff. Okay. But why does it look like this? Why do we have this really neat spacing feature out here in the infrared? Why do we have a similar kind of one going? And remember, there is a line like right about here that we just don't see in this picture, having the same sort of a spacing, and then another similar sort of spacing down here. And also remember that these are in nanometers. See right here. And nanometers are going to be related through that more complicated equation to energy. So this isn't linear with respect to energy. Something funny is going on here, but there's definitely some sort of an important pattern. That's something that started to jump out at people. So not only can it not go to any radius it wants to, it's got to go to specific ones, and these specific ones keep on giving a very specific set of lines coming off of it, very specific wavelengths. Now, matter can either absorb or give out the photons. I just mentioned that a moment ago. And when we stick some hydrogen into a lamp bulb, and we set up a slit and another slit so that it's just making a single beam of light going into the prism, we put it through this prism, we get that line right here, 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 and here that I mentioned moments ago, red, green, blue, and a violet. And if we grab some white light just as a reference so we can see where everything's at, you can see that our red line is at 656.3 nanometers. And you don't need to have these memorized. We're going to have one in the green, actually like a bluish green kind of color to it. So it's going to be 486.1 nanometers. You're going to have this very neat, like almost a cobalt kind of blue at 434.1. And just barely inside the visible, at 410.1 nanometers, you're going to have this violet line. Remember, ultraviolet starts right around 400 nanometers, so this is one that's pretty hard for our eye to make out. That's why some pictures leave it out entirely. Great, so hydrogen does something very neat. That's not totally shocking that it could have this neat kind of behavior, because it's a very simple atom, right? Hydrogen's going to have one proton and one electron flying around outside of it. When you have simple things with enough complexity, you can have some neat patterns come from it. Think of, an Etch-a-Sketch, or I forget the name of it, the one where the spirographs, where you put it into like this little gear and it makes these neat little spiral patterns. Very simple things can give some neat patterns, and you can work that backward to understand what's hiding inside. But when you start having more and more particles, well, it turns out that those patterns are going to get more and more confusing. And so if we were to look at two other atoms, mercury and strontium in this case, you can see that they both also have very specific colors that come off. But there's not really a pattern to them, the way that we were saying before. What we can say about this, though, is that each atom has a fingerprint set of lines. And it's distinctive, and every time I pick up a hydrogen atom, or a mercury atom, or a strontium atom, I get the same set of lines from it. So there's got to be something about the structure of the atom that's very specific to each atom and leads to these lines. That's a pretty big hint toward what's going on inside of their atom, and it led them toward their next invention for their models. Now, each of these atoms are always going to absorb and emit the same energy, photons. And if we're having the same photons come off, that means we're transitioning between the same levels each time. That was really the key to trying to figure out what's going on here.